OK, let's talk about a different one. Let's keep going. Let's roll some dice. Let's write a function called DiceRoll. And you'll pass in an integer for the number of 6-sided dice that you want to roll. And I will output all of the possible combinations of values for those dice. So if you do DiceRoll 2, it'll print all the combinations of 2 dice you could roll. If you say DiceRoll 3, it'll print all the combinations of 3 dice you can roll. And again, you might be thinking for loops and stuff, but I think there's some self-similarity here, right? It's a little bit like print binary, print decimal. So when I'm solving these kind of problems, I ask myself questions like, OK, this is one of those problems where each call is making a decision. Each call is doing one chunk of the work. What is the chunk handled by each call in this case? I think I've called you. Let me see if I can get something new. It hasn't helped me before today. Yeah?
You could do line dice roll and like the prefix could base that.
OK, so maybe each call handles one of the dice that we're going to roll. It'll do one die roll. So like over there, dice roll 3, maybe the first call decides that the first die is 1, and then explores all the things that could come after that, something like that. OK. And you said the prefix, we probably want to use something like that concept again here. And you said maybe it's like a set of choices instead of a string of choices. That's an interesting idea. Partly the output looks kind of collection-y, right? That's what it looks like when you print out a collection, right? So it's intended to be a little bit of a hint. And also, I mean, we're not building individual characters. We're sort of storing numbers that we've chosen. So that's a good way of thinking of it. So just before we start typing code here, basically, this is what we want to do. For each possible value the first die could have, underneath that, for each value the second die could have, underneath that, for each value the third, right? And this is what I came back to when I said, well, if you want for loops, you would sort of want a for loop for the first die, and then another loop for the second die, and another, and another, and another. And you wouldn't know how many for loops you needed until you knew what the parameters value was. That's why looping to solve the whole problem is kind of not ideal. So we want to explore all of them. OK, well, that leads to what I call backtracking. A lot of these algorithms, you make your choice and you explore what could follow that choice. And then when you're done exploring that, sometimes you need to sort of hit an undo button, you might say. And what I mean by that is you say, well, I'll explore what could happen if the first die were a 1. So you print all the things that could come after that. And when you're done exploring that, you want to say, well, OK, forget the first die being 1. Now I want to try the first die being 2. And now explore after that. And so sometimes when it comes back from your exploration, you have to sort of undo a decision or a choice you made previously. And there's lots of algorithms that have this aspect to them. A really classic example is you're looking for a way out of a maze. And so one way to solve that problem is you just pick a path and you try going that way and see if you get out. And if you don't, you undo and come back where you started and go a different way. And you just keep doing that until you find the way out or until you exhaust all the possible squares you could visit. You have to be a little careful not to revisit the same square twice, so maybe you leave breadcrumbs of where you've been before or something like that. But that's a perfectly reasonable way to try to find a way out of a maze. There's lots of things like that when you're searching for solutions to problems. So this is kind of the template of problems that involve this backtracking aspect. They're still exhaustively searching through a space, but what you do is you make a choice, you explore what could follow that choice, and then when you're done doing the exploration, you undo the choice that you made. That's the backtracking. So I have this mantra that I really like to say to students, your code should have this form. You choose, you explore, and then you unchoose. And there's variations of what that actually looks like when you write the code, but that's a good way of thinking of it. And if your code doesn't have those aspects to it, then you're maybe not doing the backtracking quite right. OK? And there's a little bit of dressing around the choose, explore, unchoose. The idea is, well, base case is there's no decisions to make. Recursive case is, well, there are some decisions to make. We're not going to make all of them in this call. We'll make one of them. So for each of the possible choices we could do for that one decision, we'll choose it, explore it, and unchoose it. So if we are doing dice rolls, and you're going to think of a picture of the different calls you could make, the idea is initially, you haven't chosen what values any of the dice will have, and there are maybe 4 dice available to roll. So the tree here forks in 6, because it's all the possible values I could have for the first die, followed by all the things that could come after that. So let's decide that the first die has a value of 1. Now we have 3 dice left to roll. Let's look at all the values that the second die could have. Well, first we'll try it being a 1. Then we'll look at there's 2 dice left. Let's try all the values the third die could have. Let's try it being a 1. Now we have 1 die left. Now we get to the point where we've chosen all of them as being 1s, and there's no dice left. So maybe we would sort of show that or output that or something like this. That sounds like a base case. And once we're done doing that, where are we at in this algorithm? Well, we just most recently chose that fourth die being a 1. We explored what could come after that, which is nothing, or just printing this. And now we're going to undo that choice and come back to here where we haven't picked the fourth die yet. And let's try a new path where instead we make the fourth die be a 2. So you sort of try it with a 1, undo. Try it with a 2, undo, this sort of thing. And so the code ends up looking kind of like this. Let me get the animation done here. It ends up looking like that. Each branch of the tree forks in 6. OK? So what's a base case? I didn't make this into Socrative. I just am going to ask the room. What would be a base case for this sort of an algorithm, do you think? Yes?
When there are no dice left available.
When there are not any dice left, right. And again, it's a classic one of those things where a lot of people say, oh, if there's only 1 die left, that's the easiest. Of course, the only thing easier than rolling 1 die is rolling no dice, right? So yeah, when there are no dice left available, that means we've made all the choices. The prefix is the full answer, basically. Think of it that way. Print it out. Great. OK, let's do it. Let's do it. So here's kind of a pseudocode of what we want to do. If there's no dice left to roll, we're done. Otherwise, for each value in 1 to 6, we'll try choosing that to be the next die value. We'll explore what could follow, and then we'll undo that choice. So how do we keep track of the choices that we made? Now, you mentioned keeping like a set of our choices, a set of the things that we've chosen so far. I think it's a really good idea. I want to amend your suggestion by 1 word. I think a set is not the collection that I would use, because a set kind of rearranges the order of the things that you put into it. And I think I want to remember that this one was the first choice I made, and this one was the second choice, and so on. So what would be a collection that would remember that? A vector would be fine. A stack would also work pretty well. Let's try with a vector. So here's what we're going to do. I'm going to exit out of this file. I'm going to rename main to OK, there. And then I'm going to open my other file, which is called DiceRoll. Oh, I hope I deleted out the solution code. Did I? Let's see. Yep, I did. OK, good. I'm so smart. DiceRoll. OK, I want to keep track of all the choices I've made so far in a vector. Vector of int, chosen, the things that I've chosen. How is that vector going to be reachable by all these sub-recursive calls that I make? Well, this seems like another case where you remember how we had like prefix up here in the heading of the function? We probably want something like that. But just because of some of the subtleties of C++, you can't use one of those default parameter values here. I think what you want to do, if you want to pass along a vector up here, what I think you want to do is write another function called void dice helper that takes int dice and also takes vector of int reference called chosen. Why by reference? Because I think we want them to share. Like if I choose, I want you to see what I've chosen. I don't want to, I want them to share. I want this to be by reference. Also, it'd be very slow if I were copying this vector over and over. I'll make a helper. And what I'll do here is I will just have the DiceRoll function that I was asked to write. I'll just have it immediately called a helper. And so the helper is what I really want to write, and the original function is the one I'm being forced to write by the problem statement. I have to keep both of them because they didn't ask me for a function that took a vector. They asked me for a function that took an int. So that's why I'm doing this. So I'll say vector of int chosen, initially empty. And I will say, let's do dice helper with the same number of dice and the chosen vector that I've created. So now in here, you guys just told me that the base case is if there are no dice left to roll. And again, I want you to think of it the same way we thought of it with the printing binary. If it says digits 0, digits 1, whatever, that doesn't mean it's a 0-digit number. It means there are 0 digits left to choose. If it says dice 0, that means there are 0 dice left to choose. So that seems like a base case that's easy to print. Maybe we'll come back to that. If it's not 0, what that means is there are some dice left to roll. And for our call, the job that our call should do is, let's handle 1 die. And what we'll do to handle that die is, for each value that die could have, we will, Marty's mantra, choose that value. We will explore what could come after that value, and then we will unchoose the value. So here's what we'll do. For each value the die could have, that's easy, right? I can say for int I equals 1 up to 6. OK, there. Now for each of those values, I want to choose the value and explore it and unchoose it. How do you choose a value? What is it that indicates choosing things here? What does that mean to choose this value? Back, yeah.
Call the recursive function again.
Call the recursive function again. Well, I would say that that constitutes exploring further things that could come after my choice. So I like making a recursive call. I'm going to call DiceHelper here under the explore part. But before I do that, I have to pick one of the dice values. I have to do some of the work here in my call. Yes, sir?
It would be adding it to the vector of interest.
Add it to the vector. The vector is keeping track of all the things that I have chosen. All the choosing gets remembered in there. Yeah, so chosen.add I. So let's add to the end. I've chosen the next die will have the value I. And then I'll call DiceHelper. What parameters do you think I should pass to DiceHelper? How many dice? Yeah, my call's worth of dice minus 1. And then the same chosen vector that now has one more thing in it we're sharing. But when we get back, like if I picked to put a 1 in there, I explored all the things that could follow that 1, and now we've returned from all that journey. I want to pluck that 1 out of there and put a 2 in its place, you understand? And then explore again, and then come back and then put a 3 in and explore again. Come back and put a 4 in and explore again. And so I basically want to say chosen.remove I, but that's not quite right because remove in a vector doesn't take the thing that you're removing. It takes the index to remove it from. So really, I should say where in the vector the thing is at. Where would it be at? It's at the end of the vector, because I added it at the end, so I remove it from the end. So we'll remove chosen.size minus 1. Remove the last thing, because that's the thing that I added. So, I mean, if you want to think about it, like, I'll run this in a second, but every call adds something to the vector, and then later removes the same thing from the vector. So the end result of every level of this will put the toys back where it found them. You know, like the vector will not grow and grow and grow. It'll grow, shrink, grow, shrink, grow, shrink. What's the base case when dice equals 0? What do you think I do there? That means the vector has got all the choices that it needs to have. It's full. There's no choices left to be made. So I should print the choices I made to get to this point. See out, chosen, endl. I think that's it. Let's try it. Uh-oh, undefined main. I think that's up here. I have to rename this one from something else to main. There. And then let me comment this out. Okay, compile. It's doing DiceRolls 4. Let me do DiceRolls 3. I think that's better. DiceRolls 3. Ooh, looky. So it prints 111, 112, 113, 114, 115, 116, and then it goes 121, 122, 123. So again, I think this is one of those cases where you might not immediately believe that it would work or see why it works or why some of the other things that you might want to write wouldn't work. And I just, you know, my favorite way of gaining a little bit of ground on that is to go print at the start of the call right here, say, you know, cout DiceHelper plus dice or arrow dice, arrow, comma, arrow chosen, arrow endl, print the parameters, print the name of the function, run it again. And I'm going to copy paste so I can do indentation in my editor here. So DiceHelper 3 with nothing chosen leads to a lot of things. That leads to DiceHelper 2 choosing a 1, which leads to a whole bunch of lines of output there. The first of those is it leads to DiceHelper 1 with a 1-1, which leads to all of these. And each of those leads to a line of output getting printed. Do you kind of see the progression of these calls? Each one is leading to 6 more, right? But when all 6 of these are done, those were the 6 possible choices I could make for the 3rd digit following a 1, 1. So after doing that, I probably need to backtrack and turn this 1 into a 2, and then repeat what 3rd digits could follow a 1, 2. And so each call is exploring, coming back, changing the last digit to the next one. Explore, come back, change the last digit to the next one. Keep doing that until the last digit has been a 6 and I've all explored after that. At that point, I'm done exploring everything that could follow me, so I return back to where I came from, and the process keeps going. So, I mean, we end up with a whole bunch of lines of output. It'd take a long time to trace through. But that's kind of generally what's going on here. And again, I'll just put it back on the Qt Creator so you can see the code. Does that sort of make sense? I mean, do you guys have questions about the code that we wrote here? Yes?
So if you wanted to keep track of all the ones, rather than like printing them out, if you wanted to store them somewhere, would you have to create a separate data structure to store those instead of printing them?
Oh, that's a really interesting question. Instead of printing them all, what if I wanted to produce them all and have them and save them somehow? I would have to pass in another reference to a collection all down this call tree that was like a vector of vectors. And I would have to add my chosen, in the base case, I'd have to add that to the vector of vectors or something like that. That would be the way to deal with that. I've only got a minute or 2 left. So let me show you one variation of this that I want you to sort of think about. I want to seed your brain a little bit before we resume on Wednesday. If we had to write a variation of this called DiceSum, where you passed in the number of dice and the sum that you want it to add up to. So don't print all of them. Only print the 2-digit rolls that add up to 7. Only print the 3-digit rolls that add up to 7. You understand what I'm saying? You could imagine a very small change to our existing code that would do this. And I've only got a minute, but I think I could do it if you'll let me. I'll copy this, and I'm writing DiceSum. So I'm going to write void DiceSum helper. It takes int dice, int desired sum, and vector of int reference chosen. And I paste all this in. The only difference is I'm going to call DiceSum helper. I'm going to pass the desired sum. You understand? I'm just making kind of minimal changes here. What's the only difference I need to make to this code so that it won't? Right now, it's still going to print every possible roll, right? Minimal change. What do you say, sir? Yeah.
In the base case, if you add a condition to check the sum of the elements of the vector.
Do some kind of add up the sum of the vector. If the sum is to what I want, then print it. Totally works. Bad solution. Very inefficient. We will talk about why it's bad, why it's inefficient, how to fix it Wednesday. So have a wonderful day.